Okay, graphs of tangent, cotangent, cosecant, and secant functions. Okay, I'd like to brainstorm everything we know about y equals tan x. So in other words, what do you know about tangent? So I'll take anything. You guys can tell me anything you know about tangent. We've already done domain and range the other day. So what do you know about tangent? We were playing around with our calculators, right? Anything you remember from that activity, too?
Y equals tan x plus 180 is equal to y is equal to
Oh, yeah, we did have a rule. So we said that tan x is the same as tan of x plus 180. It's true. This is a really important thing. What this means for our graph is when we're done sketching it, if we shift it by 180, it won't matter. That's what it means. It will look the same. Very good. Okay, we would say that the period of tangent is 180. That just means that if you shift it by 180, you cannot even tell. It looks just like it did. This is also true for x minus 180, by the way. We didn't write that, but it's true. Any other factoids, little things we learned? Do you guys remember typing tan 89 and tan 89.9, that sort of thing? What was that?
Oh, well, it gets exponentially larger. Well, not exponentially, it just gets a lot larger every time you go closer to 90, but don't reach 90 because 90 is undefined.
Yeah, we said that tan of 90 is undefined, right? We did say that. But we said that if you do like tan 89, tan 89.9, of course we're talking about degrees here, tan 89.99, these were going like 57, 570, remember? 5,700, I'm rounding. But these numbers were growing. That is an important fact to know for today, okay? So one way to say it is, as x approaches 90 degrees, and this little minus means from the left. That means from numbers slightly less than 90. So this symbol, x arrow 90 minus, this symbol means 89.9, 89.99, 89.999, 89.99999. That's what that little minus sign means, okay? Because you can also approach 90 from the right. 90.01, 90.001, 90.0001. This is from the left. As this happens, tan x goes to infinity. What else did we talk about with tangent? Yes? It's an odd function. Yes, it's an odd function. That's important because that tells us the kind of symmetry we have. We have what kind of symmetry? Origin. Yeah, origin symmetry. That means if we graph one period, we can figure out where the other ones go for free, just knowing the symmetry alone. Okay, so that's just some little facts. This is probably good enough. Oh, maybe we could write down the domain and range real quick. Do you guys still have those tables? Take a look at your tables. Domain and range. What was our domain? Yeah, theta does not equal, right? 2k plus 1 times pi over 2. In other words, no odd multiples of pi over 2, or you could say odd multiples of 90 are forbidden, right? Odd multiples of 90 degrees are restricted. But the range was all real numbers. The range is all real numbers. Okay, that's good enough. Let's just go ahead and sketch our first tangent graph. Now you can peek in the book. You can ask your calculator to graph it. Okay? You can make a table. But I'd just like to piece together what we've learned so far and a little common sense to come up with a graph. Okay, so here we go. You don't have to graph everything you see, just a couple points is good enough. One thing we know for sure is that pi over 2 is forbidden, right? So there's a vertical asymptote right here. That's 90 degrees, forbidden. 3 times 90 is also forbidden, because that's an odd multiple of 90. In other words, 270, or 3 pi over 2, this is forbidden. If there's origin symmetry, then these two asymptotes will show up on the left side as negative pi over 2 and negative 3 pi over 2, which is also negative 1 times 90 and negative 3 times 90 degrees. All odd multiples of 90 are prohibited, even the negative odd multiples. Okay, so there's what the graph looks like. And let's talk about the unit circle for just a second. Remember that on the unit circle, the purpose of the unit circle is to help you find sines and cosines quickly, right? But I had suggested that maybe you could go around your unit circle and put tangents on here as well. Did anyone ever do that? I mean, raise your hand if you actually went around your unit circle and added in the tangents. Excellent. Okay? If you haven't done that yet, that would be a really good thing to do before the quiz.
Is this open?
It's open notes, open book, just like last time, okay? So the more facts you have ready to go, the faster you'll work. Time management's the issue, right? Time management. So if you did go around, you probably have written that the tangent here is 0, and this is undefined, as you know. And tan 45, I'll bet you got that one on there. That's an easy one. Tangent is uno. The reason is x and y are both the same there, right? So when you divide them, you get 1. Okay, so at pi over 4, we have 1. At 0, we have 0. At pi over 2, it's undefined. So I just did these 3 points only in blue. But this will kind of help me get things started. I know that when the angle is 0, tangent is 0. But when the angle is 45 degrees, tangent's 1. So halfway between the y-axis and my first asymptote, I have a y value of 1. Right here, that's the point 45 degrees, comma 1, or pi over 4, comma 1. Super important point. The odd symmetry of the graph, the origin symmetry, dictates that we have to have one here as well. So you remember when we did the cubic graphs and the other graphs, I told you to memorize the 3 points, 3 amigos. These are the 3 we're going to memorize for tangent. They are negative pi over 4, comma negative 1, the origin, and pi over 4, 1. If you understand symmetry, you only need to memorize 2 of them. Right? The third one will be for free. Okay. All right. So your graph is going to look like this. Shooting up towards infinity as we get closer to 90. Remember what the calculator was doing? That is the fundamental period for tangent. The fundamental period. That means that's the part you memorize. Okay, boy, that sure looks familiar. It looks a lot like another flashcard we've made. What does it look kind of like? What does it most resemble? It looks kind of like x cubed. Let's talk about the differences. Okay, first of all, x cubed didn't have asymptotes, right? Also, your x cubed graph, don't draw it, but I'll draw it, because I can always press undo. Our x cubed graph actually looks more like this. It passes through the point negative 1, negative 1, which is actually really close to this blue point, negative pi over 4, negative 1. Negative pi over 4, that's 3.14 divided by 4. We're talking 0.8-ish. And the green point right next to it is at negative 1, negative 1. So it's very close. And of course, 1, 1 is really close to pi over 4, comma 1. But what is it about the shape that's different? This is really important. Yeah, look at the red curve. The red curve is not flat in the middle. When you take calculus, flatness like steepness and flatness, that is one of the most important topics of all. So it's good to get this in your mind early, that one of the main differences between this and the graph of x cubed is not really the positions of the 3 points you memorize, it's the shape. This line right here, if you drew it, what do we call this kind of line again? A tangent line. That thing should have slope 1. Okay, slope 1. So if you could sketch a little line right there, it's supposed to have a slope of 1. Okay? So I want to just show you something real quick, something you might not have thought of. This is a tangent graph. If I graph a sine wave right on top of it, watch. Let me make it a little easier to see. Look at the origin. They're almost exactly the same.
They both have slope 1.
That's right. They have the same slope behavior near the origin. Both the sine wave and the tan wave have very similar slope. If I were to zoom in and say, like that, you would be like, oh, y equals x. Looks like y equals x. Looks like line y equals x. Or someone would say, no, that's probably the sine wave. Someone else say, no, that's tangent. They're all pretty much the same.
So if
near
you
the
were to
origin.
shift the cosine wave. on
Cosine's
the
different. Cosine's shifted, so wouldn't even be in this picture. But you guys see what I'm saying? The shape of the graph. Any artist knows it's not enough to just draw things in the right place. You got to get the right shape, right? So this is just think of it as art. You got to get the right direction on your curve there. Pretty important. Okay. In fact, I don't think there are any horizontal tangents anywhere on this graph. If you were to graph lines that were tangent, every one of these has a positive slope. That is very interesting. That will be very important later when we do the inverse graphs. This thing will be laying on its side at that time. Okay, that's enough for tangent, except to say that there's more of them. There's a piece here, of course, and a piece here, because this thing just duplicates itself, as you know. One period is enough to memorize, but it's never the full graph, right? Okay, so many, many, many periods. They all look exactly like the one in the middle. So memorize the one in the middle. Let's go on and talk about cosecant. So as you know, cosecant means, what does cosecant mean? Like by definition, what is cosecant? It means 1 over sine. This is what it really means. Okay, we're not going to brainstorm this. We're going to use the graph of sine to help us draw the graph of cosecant. Okay, so think with me here. If sine x goes through the x-axis, in other words, if sine x is 0, that would be these points right here in black. If sine x goes through 0, then that means cosecant won't exist. So these 3 black points suddenly become our asymptotes. So we have vertical asymptote right here. Wherever sine of x has an x-intercept, cosecant of x has a vertical asymptote. That's really important. Okay, that's the first thing you need to know. Bless you. The other thing we need to know is that when sine x is 1, that's these points here in black, or negative 1. So this point here, or this point here, when sine x reaches its extreme values, 1 or negative 1, the reciprocal of 1 is 1, right? And the reciprocal of negative 1 is just negative 1. So we can see that what's going to happen is our graph for cosecant will touch these 2 points as well. Okay, now if you go back in your notes, you'll remember that the range for cosecant is the exact opposite as the range for sine, right? So while sine is wiggling between negative 1 and 1 vertically forever, cosecant says, I can't do that. I'm 1 over a decimal. So basically you get this shape, like this. Like that. All right, those are not the only two, right? I mean, we have more of them. In fact, this is one block, you could say, of an infinitely repeating pattern. The pattern goes like this. Frowny face, happy face. Frowny face, happy face. Oops, I missed. So you're basically going to have one pointing down and one pointing up. And this just goes on forever. Okay? There'd be one pointing up here. And one pointing down over here. And between every one of them, there's an asymptote. So there's a vertical dashed line. So what really happens is it suffices to know the graph of sine, because if you know the graph of sine and you know that the x-intercepts are your asymptotes, you can just piggyback your cosecant graph right off the sine wave. It's not very hard to draw at all if you know that trick. Okay. Any questions on that? Okay, so where is the fundamental period? Like, which piece do we pick to call the one you memorize? This is an important question for later, so we don't need to answer right now. But one thing is for sure, you have to memorize one happy and one sad to get the full effect of the graph. If I ask you to draw one period of cosecant, and you only draw one of these parabola-looking things, you didn't answer the question. This is made up of a smile and a frown, a smile and a frown, a smile and a frown. So you have to have one of each to call it a period. That's really important. It's kind of like when you go on the beach and you see footprints, right? And someone says, hey, circle a set of footprints on the beach. And you're looking at the footprints on the beach. All right? Not a very good artist. If you're looking at these footprints on the beach, you need to circle a right foot and a left foot if you're going to call that a set of footprints. Okay? You need to pick one of each. That's a set of footprints, right? You cannot say that a set of footprints is one print. No. A pair of prints is a set of footprints. You understand? Okay. Same thing with this. You got to pick two, one of each, an up and a down. We want to do the same thing with the graph of cosine to get the graph of secant. It's not new. It's the same thing. For each root, you draw an asymptote. I should say for each x-intercept, you draw an asymptote like this. So in this window, I can get, looks like I'm going to be able to get 4 of them. When you guys make your flashcards, just do the examples from the book. I mean, look at your graphs in the book. They're beautiful. Mine are horrible. Okay, so you'll have a piece like that, and a piece like that, and a piece like that. I could have you memorize multiple dots on each piece, but I think that's overkill. I don't think we need that. I will say this, these are less like parabolas and a little bit more like x to the fourths. They are relatively flat in the middle. Sort of. Not too flat, but not too sharp either. They're certainly not parabolas, but they look kind of like them, or x to the fourths. Okay, your graphs in the book are much better than mine. You still need to know the domains and ranges really well for Wednesday's quiz, so make sure you have those tables handy, and on Friday you will be doing that without the tables help. Domain just means anything except those asymptotes is the domain. Range is anything above 1 or below -1. Okay, our last graph is the graph of cotan, and for that we can use the graph of tan. In case you're having trouble seeing, this was at pi over 2. This is 3 pi over 2. Same asymptotes as tangent had. Okay, so I'm ready to move on to tangent. You can get the rest of the details from your textbook. But the textbook takes, a full paragraph to explain that the roots are the asymptotes, So it's more verbal. If I do it in class. Okay, let's go to this now. Cotan. So what is the cotan graph going to look like? Let's move these out of the way. derivatives will be the asymptotes. Same rule as before. Okay, so the x-intercepts are here. That's going to be an asymptote. There'll be an asymptote on the y-axis. That's interesting. And there's one at pi. This totally agrees with the table we made earlier last week when we said that these were forbidden angles for cotangent. I'll label those for you. This is at 0, and pi, and negative pi. You don't need the black graph, really. So the pieces we draw have to fit between the red dashed lines, and it turns out they look kind of like upside down tangent graphs. Actually, that's exactly what they are. They're upside down tangent graphs. Oh, by the way, your what once were asymptotes are now your x-intercepts. Let's put those on. So for every vertical black dashed line, those are just x-intercepts. That might help you see better. Okay, so here comes the graph. Most people agree that that's the fundamental period. Not everyone agrees on that. Here's the next period. It would go like this. And this piece here. Something like that. My graphs don't have to be perfect. I just need to show you that it's basically upside down in its shape and shifted in its position. Okay, so see if you can fill in this statement. Fill in the blank. A cotan graph is related to the tan graph through two transformations. There are two transformations you can apply to that black graph to produce the red one. Can you figure out what they are? Don't shout it out, but see if you can figure out what goes in the blanks there. Just write it down for now. Some people will see it real quick. There's two. If I do two different things to that black graph, it will produce the red one. And then see if you can fill in the blanks. Okay, does anyone see what they are? Raise your hand if you think you know. Two hands. All right. What do you think?
Is it negative 110 x plus or minus 180 degrees?
You're really close. So there's definitely a negative there. In other words, a cotan is an upside down tan, or a tan is an upside down cosine, or cotan. Good. Cotan is an upside down tan. Excuse me. And then you said there's a shift.
And then I said x plus or minus 180 degrees.
Okay, if we shift the black graph 180 degrees, it will end up right on the black graph again.
The red graph.
Plus 99.
Is it, wait, is it 90?
It's 90. Yeah, it's x minus pi over 2. So if we take the black graph and we flip it upside down and shift it to the right by 90 degrees, that is the cotan graph. So you're welcome to memorize that. That way you don't even have to think about the cotan graph. You just be like, oh, I'll just take my tan graph, flip it over, and slide it over. Done deal. So usually what helps people the most is to know where the roots are, to know where the asymptotes are, and that's usually good enough. And that's true for the last three graphs we did. So that graph, if you just know where the x-intercepts and the asymptotes go, same thing with that one, and that one, that's good enough. Actually, on cosecant and secant, all you need to know is that it piggybacks off of the parent function, sine and cosine respectively. So memorize tan today, okay, if you can, try to get that in your brain, especially those three blue points. And the rest can be done by transformations. So You guys have note cards to make, you have some problems to do. Some of those are just flash, some of those are just matching those green problems I put on the board. But that's a really good exercise for your brain. So